Welcome to Innovate and React. I'm Kevin Hares, and in today's episode I will take you to the beginnings of natural product research, how compounds that are coming from nature can help to cure cancer, and how chemists can help to bring them to the market. Plants have probably been used as medicine since human existed. However, they were not really studied for their active compounds for a very, very long time. In the 1950s, public pressure for doing something about cancer was rising, which kicked off the foundation of the National Cancer Institute in the US. Funding increased from 0.5 million to 14 million in 1951. So cancer research has been well funded at that point. However, it was not well organized in the beginning, and that slowly changed over time. For example, most of the samples that were tested in the early 50s to evaluate compounds for potential cancer agents and biological activity were done at the Solon Kettering Institute. Not enough for the rising demand for research requests. To fight this shortage of processing capabilities, the Cancer Chemotherapy National Service was established in 1955 and about tenfolded the screening capabilities. So now they could process over 30,000 samples per year. Starting with known synthetics and fermentation products, they began to screen extracts of natural products in the 1960s. Those were complex mixtures of unknown compounds and structures, so it was really not easy to figure out what was in there, what was really the active compound. At that time, the organizer of the NCI, the National Cancer Institute, plant program was Jonathan Hartwell, who was the perfect choice to head this plant screening project because he had wide experience in natural products, chemistry, and he believed that plants had chemotherapeutic potential. Hartwell compiled a comprehensive work on the traditional use of plants to treat cancer, complete with references to the literature of Asian, Chinese, Egyptian, Greek, and Romans, which all have been using plants to cure all kinds of diseases and also cancer, although it might have been not known that it was cancer at the time. Hartwell laid his focus on what we call cancer plants, the plants that have shown biological activities in a study in the 1950s. Juniperus sabina showed some anti-cancer activity, but did not make it further as the results were not strong enough. But this was the start for his search in the conifer family. So he started to look deeper in this kind of trees. Crude extracts have been shown potential and became candidates for fractionation, where the unknown crude extracts were isolated in their individual compounds. Hartwell convinced the chemist Monroe Wall to send him more samples for screening, who was working on agriculture alternatives for products like rubber, which were crucial for the war efforts at the time. Indeed, about 1 year after they met, one plant named Acuminator showed potential activity. So, working together with different institutes had already shown potential. Monroe Wall wrote in his work at the Eastern Regional Research Laboratory, the joint effort of chemists and botanists proved to be a good model for future programs. Indeed, it firmly established the fact that those cooperations between chemists and botanists were required for a successful natural products program. So they had to work together, the chemists and the botanists. those who know the plants and those who might know how to extract the active compounds. They were able to obtain 20 kilograms of the wood and bark of the Camptothecin acuminata and started fractioning the crude extract. Each fraction was tested for biological activity, which is why the process was named bioactive direct fractionation. This means that from each step, the fraction which had the most biological activity was worked on next, so they could streamline to focus on the most active extracts and narrow down where the active compounds are. In the 1960s, this was a difficult and slow process, which required great skill and intuition on the part of the researchers, using equipments that can now be found in only museums. This is due to chemists not really working with biological compounds that much back in the days, and they had to come up with a lot of new techniques that are almost forgotten now. After years of work, they managed to isolate Camptothecin, which showed activity against different types of leukemia. The research on the isolation and structure of Camptothecin was published in 1966 in the Journal of American Chemical Society. The first paper Varney and his colleagues published on a natural product with anti-cancer potential. Varney describes the isolation of Camptothecin as the most exciting scientific event in his life, because Camptothecin showed such promising anti-tumor activity, the NCI decided to proceed with clinical trials. In the mid-1990s, so almost 40 years after the whole plant program started, two Camptothecin analogons, topotecan and irinotecan, received FDA approval for use against ovarian, lung, breast, and colon cancer. So this really showed that natural products can have benefits. And this really shows that we can find really potent drugs also in nature, in trees, for example, or other kinds of extracts. We can use those after many, many tests, because when something is from nature, it doesn't always mean that it's better than something synthetic. If you think about all kinds of toxins that come from nature, we know that there are also compounds that are bad for us, but there are also some that can help us. So it's not a clear line between natural and synthetic, which is better. However, the combination of both might also be great, which is part of the next story I want to tell. Before I continue, a quick break for two things. First of all, thank you for tuning in and listening. Secondly, if you like the show, please follow Innovate and React on your favorite podcast app. This really helps me to grow and get new guests on the show to continue. Also, let me know if you have topics that you would like to learn about, or if you want to talk about your research in the podcast. You can find the contact info in the show notes. Thank you for your time, and back to the episode. Another interesting conifer was discovered by chance as botanist Arthur Barclay brought samples from the Pacific Yew tree, Taxus folia, to his lab. Both of his samples were sent to the Wisconsin Alumni Research Foundation for extraction. Stem and fruit, as well as stem and bark. The bark showed activity, so Hartwell ordered his contacts from the USDA to collect larger quantities. On September 8th in 1964, Barclay returned to the spot where he had originally collected his sample and bagged 30 pounds of the bark from T. brevifolia, which was shipped to Monroe Wall at the research Triangle Institute after other laboratories turned it down. These laboratories were reluctant because plants that exhibit high toxicity turned out to be poor drug candidates since they're toxic to everything, killing the tumor cells as well as healthy ones. So it was not selective enough and toxic in general. But Wall was interested because of his experience with Camptothecin acuminata, which was highly cytotoxic, but from which his group had isolated a compound that showed great promise in the previous story. So they again began the bioassay directed fractionation. And after 2 years, they finally managed to isolate a crystalline compound. Wall named it Taxol, after the Latin name of the tree it came from, Taxa breviola, and ending "ol" as they knew it contained hydroxy group, which are alcohols, and they are usually named with the ending "ol." However, for this compound to be used as a treatment, the newly discovered compound needed to be characterized and confirmed in clinical trials. So the need for more and more bark was there, and this was even compounded by the fact that the yield of Taxol from collected bark was very low. This showed the process to determine the molecule structure. This slowed the process to determine the molecule structure because you need some quantities to prepare samples. Some are samples that are destroyed while characterizing, so you need some quantity of it. To definitely learn the structure of Taxol, Wall and Wani used mass spectrometry, X-ray crystallography, and NMR spectroscopy. At the time, this technique was in its infancy and needed larger quantities than we are used to today. These various tools produced a molecular structure with a formula of C47H51NO14. Wall and Wani also discovered Taxol was two molecules in one. Basically, a connection between a large molecule and a small tail, which was a side chain. Using all these informations, in 1971, Wall, Wani, and co-workers could finally publish their results on Taxol in the Journal of American Chemical Society as a communication to the editor, in which they stressed the anti-leukemic and anti-tumor activity in the newly isolated molecule. However, NCI was not convinced to continue with animal trials because the isolation and extraction of Taxol from T. brevifolia was difficult, and the tree was not really that prevalent, producing only very small amounts of the compound. Each tree yielded only about 2 kilograms of bark, and in the early days of testing, it needed about 12 kilograms of dried bark to obtain half a gram of Taxol. So the yield was very low. And the biggest problem of this is that the bark is kind of a finite resource. It is crucial to the tree's survival, so if the tree is stripped of its bark, it dies. And then it takes a very long time for it to grow back. So Taxol was forgotten on the shelf literally for a while until it was revisited in 1978 when new tests were developed. The new B16 melanoma tests, which Taxol was surprisingly active against. So in November of that year, they showed the ability to cause considerable regression in a mammary tumor xenograft. It's basically putting tissue from one species, putting it into another species. And what they did is they managed to breed a type of mouse that basically had no immune system. And then they would take a human tumor and transplant it into these mice and then treat them with Taxol or other compounds and see how these tumors would respond, which increased the interest in Taxol again. So they could show that Taxol was acting against human tumors inside a mouse. And finally, the interest in Taxol increased again in the year after, when Susan Horwitz demonstrated that Taxol's mechanism was completely different and unique and new to scientists at the time. Previous compounds kill cancer cells by inhibiting their division. So cancer cells uncontrollably divide, and that is what makes them cancerous. So these compounds before Taxol were all just trying to inhibit this cell division. They did this by preventing the production of the ultrafine filaments called microtubules that enable cells to divide. Cells manufacture millions of these microtubules and use them as a building block for the new cell. When a new cell breaks off, these microtubules basically become fragments of the protein tubulin. Before Taxol, anti-cancer agents would work by inhibiting the polymerization of tubulin to form these microtubules. Hence, the cell could not divide. Horwitz discovered that Taxol worked differently. Instead of preventing the formation of microtubules, it stimulated their development. Cells treated with Taxol began putting out so many of these microtubules that they were unable to coordinate the cell division. So they were basically crowded with all these microtubules. As a result, the cell dies because it continuously tries to replicate but can't. As a result, the cell dies because it continuously tries to replicate their DNA, but it cannot divide. So Taxol was kind of a miracle drug then, because it was completely new. The demand was high. They wanted to put it on the market as fast as possible. However, as mentioned before, the supply was very limited because of the origin of the compound, the bark of a tree which slowly grows and will die when the bark is harvested. If Taxol were made available to all the victims of ovarian cancer, the institute would have to produce 240 pounds of the drug. That would mean killing 360,000 Pacific Yew trees. And already in 1977, harvesting 1,500 trees for the initial testing led to big concerns from environmentalists. This giant number of trees would probably eradicate the whole Pacific Yew tree population. So there had to be an alternative, which encouraged many chemists to synthesize the molecule in the lab all over the world. Different groups started in trying out new methods, new synthesis routes. But the molecule is really complicated. As I said before, when they first elucidated the structure, it contains one big compound and a side chain. So synthesizing them with all of these chiral centers and putting them all into place was really difficult. I will link a picture to the compound in the show notes. The first success story came from France, where Pierre Potier looked at the semisynthesis. Semisynthesis meaning trying to use already some compounds which come from nature in that case. Specifically, the needles of the ubiquitous Taxus baccata, or English Yew. Potier extracted 10-bactein-3, commonly known as 10-DBA, The English Yew is loaded with this compound, which made the extraction much easier. And this compound is the complex core of Taxol, minus the relatively simple side chain. Much easier to synthesize than the core. Most importantly, 10-DBA comes from the needles, a renewable resource. They can be harvested without killing the tree. After several years of trying, Poitier and his colleagues succeeded in marrying 10-DBA to a synthetic version of the tail to achieve a semi-synthesis of Taxol. This accomplishment led to many different paths to achieve this semi-synthetic version of Taxol. Eventually, Robert Halton and colleagues at the Florida State University developed a commercially viable semi-synthetic procedure, which, in my opinion, is always a point that is very difficult if you're only looking at the synthesis itself. So if you think about the synthesis and use very complicated procedures that cannot easily be upscaled, then the whole synthesis will be difficult to produce larger quantities. And I already have talked to other scientists in previous episodes about this, the scale up of a reaction. It's really crucial to make a profitable and working synthesis that can also be done in the industry setup. Then after that, Taxol passed all the clinical trials. With the new developed semi-synthetic route, it could be viable and marketable drug. Bristol Myers Squibb worked out a deal with Halton to use his semi-synthetic synthesis and began production. So finally in December 1992, almost 30 years after USDA botanists first sampled, and more than 20 years after Wall and Twani reported the isolation of the structure of Taxol, the Food and Drug Administration granted approval for Taxol's use against refractory ovarian cancer. This really shows how complicated this process is from when a compound is discovered all the way to it being a drug on the market. Not only does it have to have the effects that we want for the drug to have, it also needs to be producible in a large scale, so it can be a profitable drug. Otherwise, no company would ever try to make it. And this really takes a long time and a lot of research efforts, which also is why a lot of new drugs are expensive. Since that time, Taxol also has been approved for the use in treatment of breast cancer and AIDS-related capsosis sarcoma. In the end, this really is a success story for natural products. And the semi-synthetic route already has a big advantage over the extraction of the Pacific Yew tree. It becomes much more available since the needles can grow back and are more sustainable. However, it's still a laborious process, and it would be much more convenient if the whole molecule could be synthesized in the lab. And in an upcoming episode, I will talk to a natural products chemist about all the fully synthetic ways to synthesize Taxol. These also called total synthesis came after the big success of the drug and motivated many researchers to improve the synthesis. Because with such a successful drug, a lot of funding was available for the research. A lot of funding was available for this research. So the story of Taxol is a great example for natural products that come from nature, but their synthesis improves the way of getting them and makes them much better available so it can help more people. Thank you very much for listening. Don't forget to follow Innovate and React on your favorite podcast app. This really helps me to grow the show and get new guests on to continue. Also, let me know if you have a topic that you would like to learn about, or if you want to talk about your research in the podcast, you can find the contact info in the show notes. Also, now you can support the show and keep me caffeinated by buying me a coffee. Also, the information for that in the show notes. Thank you very much, and until next time, keep innovating and stay curious.